Hello everyone. Very good evening to all of you. Welcome to PW Gulf. So today is our ultimate recap session of the chapter Newton's Laws of Motion. We'll be covering all the important topics of this chapter. So let's start what we'll be covering today. So we'll be doing what is force, inertia, linear momentum, impulse, change in linear momentum, relation between linear momentum, force, impulse. Okay, then we'll be doing Newton's laws of motion and their application in the study of motion of connected bodies. Okay, so let's start with the first topic, force. Now what is a force? Have you seen that a book is lying on a table? You just push the book and the book moves forward, or you pull the book comes towards your side. So what is force? Force is any kind of push or pull which is acting on the body. Okay, so force is any push or pull which can change the state of the body. What happened? You applied a force, body moved forward, state of the body changed. Body was earlier in state of rest, now it is in state of motion. Okay, so force is any push or pull which can change the state of the body. Force is an external agent. Okay, it is an external agent capable of changing the body's state of rest or motion. It is an external agent which is capable of changing the state of the motion. Okay, now force is a vector quantity. Okay, force will be a vector quantity because we apply a force in a particular direction. Okay, it has both magnitude and direction. So force is a vector quantity. Okay, force is a vector quantity having both magnitude as well as direction. Now what is the unit of force? SI unit of force, SI unit is Newton. Okay, SI unit of the force is Newton, denoted by capital N, and CGS unit of force is dyne. Okay, CGS unit of force is dyne, and the relation between them is that 1 Newton is equal to 10 raised to the power 5 dyne. Okay, 1 Newton is equal to 10 raised to the power 5 dynes. This is the relation between the SI unit and the CGS unit. Okay, so what we have, force is any kind of push or pull which can change the state of a body, and it is a SI, its SI unit is Newton, CGS unit is dynes. Now if we write the dimensional formula, dimensional formula for force is MLT minus 2. Okay, dimensional formula of force is MLT minus 2. Now suppose we have a particle on which numerous number of forces are acting. Okay, this is my force F1, this is my force F2, this is my force F3. So many forces are acting on a particle. Then what will be my net force on the particle? Okay, what will be my net force on the particle? Total force acting on the particle will be what? Force is a vector. Force is a vector. Vectors are not added by scalar addition. Vectors are added by vector addition. So net force on the body or particle will be F1 plus F2 plus F3. Okay, net force on the body will be F1 plus F2 plus F3. Force will be added vectorially because it is a vector. Okay, so let's see what force can do. If we have a non-zero resultant force, it means some net force is acting. If we have a non-zero resultant force, which means net force on the body is not zero, there is some force which is acting on the body. What it can do, it can change the speed. Okay, it can change the speed. A body was earlier moving with 2 meters per second, you pushed it and it started moving with 5 meters per second in the same direction. So it can change the speed, it can change the direction of motion. If a body is moving in this direction and you push it like this, body will start moving in this direction also. So its path will be a curved path. Okay, force can change the speed, force can change the direction. It can change both speed as well as direction. It can change both speed and direction. Okay, force can change both speed and direction of motion. Okay, next is it can change the shape or size of the body. Okay, it can change the shape and size. Suppose we have a ball, we applied a force on it. What happened? You have the sponge ball in your hand, you applied a force on it, ball's shape and size changes. Okay, and if you have a rubber band, you expand it using some force, what happens? Its shape and size changes. Okay, so force can change the shape and size of the object as well. Okay, now let's see inertia. What is inertia? Have you wondered why a object is lying on a table, and until and unless you make it move by applying some force, it will remain on the table in the state of rest? Okay, why so? This is because of inertia. This is because of inertia. One more example: when you are moving some heavy object like sofa or almirah, you apply some force, object doesn't move. You apply some force, object doesn't move. Why such thing happens? When we are moving in a bus and suddenly brakes are applied, we fall. Okay, why such things are happening? This is all due to inertia. What is inertia? Every body has an internal tendency to maintain its state, whether it's the state of rest or state of motion. Okay, every body has its internal tendency to maintain its state. That property of the body is called inertia. Okay, so inertia is the property, it is the property of a body by which it maintains its state. Okay, it is the property, it is not a measurable quantity, but we can get an idea that why a heavier body is having large inertia or lighter body is having lesser inertia. See, you have a small ball of mass m and a huge large box of mass capital M. Okay, which blocks or which block is easier to move? You apply some force and you will check which block is easier to make it move. In which process we have to apply less force. Okay, or in other words, we can say that which block will move easily on the application of force? Obviously lighter one will move easier. Okay, it is easier to make it move. Now when we are making it move forward, or when we are keeping this when we are changing its state, earlier it is in state of rest, now when we are making it move forward, it is in state of motion. So when we are changing the state, which condition we have to apply lesser force to change the state? In the lighter block we have to apply lesser force. So mass is a indirect measurement. Okay, mass is a indirect measurement of inertia. Inertia is a property. Okay, but property also we have, just like, see, elasticity is a property. This rubber band is more elastic, this is stiff. Okay, it is a property, but we can get an idea about it using the application of force, which is easier to stretch or compress, that is having more elasticity. Okay, so similarly, inertia can be measured using mass. Mass is a measure of inertia in translatory motion. Okay, more the mass, more will be the inertia. More the mass, more it will be difficult for us to change the state of the body, hence more is it inertia. This body has more tendency to maintain its state of rest or motion. Okay, so more the mass, more will be its inertia. This is all about inertia, that inertia is the tendency of the body to maintain its state, or we can also say that it is the inability of the body by which it cannot change itself, its state of rest or motion. A block will remain on rest until and unless we apply some force. Okay, by itself block cannot start its motion or cannot stop its motion. Okay, so what we have is, it is the ability to maintain state or inability to change the state. Okay, now inertia is divided into three types: inertia of rest, inertia of motion, and inertia of direction. Okay, so let us see inertia of rest. It is the inability of a body to change its state of rest. Okay, which state it cannot change? Its state of rest. By itself is called inertia, or we can also say that it is the capacity of the body to maintain its state of rest. Okay, it is the capacity to maintain its state of rest. What is its example? When a bus at rest starts suddenly, okay, we fall backwards because body is in state of rest, and when the bus starts, our feet come into motion, but the upper body tries to maintain its state and we fall backward. Okay, next is inertia of motion. The inability by which it cannot change its state by its state of motion by itself is inertia of motion, or capacity to maintain its state of motion. Example: when a moving bus stops suddenly, we fall forward because a body has a tendency to go in forward direction in the motion of the bus. Okay, body doesn't want to change its state. Next is inertia of direction. Inability of a body to change its direction of motion by itself is called inertia of direction, or capability of the body to move in a straight line. Okay, capacity to move in a straight line without changing its direction is called inertia of direction. Example: when a bus takes a circular curve, we always fall outside the curve. Okay, we always have a force acting on us radially outwards. So when a bus is taking turn, passengers inside it for experience an outward force. Okay, because in a circular motion we have a tendency to move in the straight line, but we are taking a curve, tendency is to go in this direction only, so we fall outwards. Okay, so this is inertia. Now let us see linear momentum. So before studying linear momentum, let's have two cases. Okay, I have two balls. Okay, one is my soft ball, one is my soft sponge ball, and the other one is, or I'll say, this is a lighter ball of small m, and this is a metal ball, all of mass capital M. Okay, this is a soft ball of mass small m, which is lighter, it is lighter, and then we have a metal ball of mass capital M, or we can also have a metal ball of mass small m and a metal ball of mass capital M. Okay, we are dropping it on a glass plane. Okay, we are dropping both these balls on a glass plane from the same height. Okay, these balls are being dropped on the glass plane from the same height. Now if I drop the small m mass having ball, okay, if I drop ball number 1 and see what happens, glass doesn't break. Okay, glass doesn't break. But if I drop the heavier ball, glass breaks. Okay, if I drop the heavier ball, that is 2, glass breaks. Then again, next situation, we have a bullet. Okay, we have a bullet. Now bullet is first thrown with hand. Okay, first thrown by hand. In first case, we throw a bullet by using our hand. Okay, first case we throw a bullet by using our hand. Next is, this bullet is fired from a gun. Okay, This is fired from a gun. Okay. Now this bullet is first thrown with hand, and next case it is fired with the gun. In which case we will have more damage. Okay. If it strikes a target, let's say some plate or something over here, then in which case we will have more damage? In first case. Okay. In this case we will have, oh sorry, in this case we will have lesser damage, and in this case we will have more damage. Okay, more damage, and in this case we will have more damage. So why such thing is happening? Okay, we are dropping them from the same height but their mass are different. Okay, in first case their mass are different but velocities at the point of striking the ground or striking the glass plane, both will have the same velocity under root 2gh if they are dropped from the height h. Okay, now velocity is same, mass is different, we have different effects. Second case, mass is same, velocity is different, we are having different effects of motion. So what is linear momentum? So linear momentum tells us how much motion is contained in a body. Okay, how much motion is being possessed by the body, or what effects it can have. Okay, same mass, different velocity, different effect. Same velocity, different mass, different effect. Okay, so its motion will depend on its mass and velocity. So linear momentum is a measure of quantity of motion possessed by a moving body. Okay, it is a measure of quantity of motion possessed by a moving body. Now see, if mass is more, we have more effects of the motion, or we can say that motion contained is more. And if we have more velocity, then also motion contained is more. So it depends on mass and velocity. So linear momentum is the product of mass and velocity. Okay, linear momentum is the product of mass and velocity. So we will write linear momentum as mass into velocity. Now velocity is a vector, so linear momentum will be a vector. Okay, linear momentum will be a vector. It is also a vector quantity. Okay, it is also a vector quantity. Its SI unit will be, mass is having kg, velocity meter per second, so its SI unit will be kg meter per second, and its CGS unit will be gram centimeter per second. Okay, gram centimeter per second. Its dimensional formula will be MLT minus 1. Okay, MLT minus 1. Now it is a vector, so it will also be added vectorially. If we have a system of 3 particles, each one is having momentum p1, p2, p3, so total momentum of the system will be p vector 1 plus p vector 2 plus p vector 3. Okay, so now let us see how it depends. So p is equal to m into v. Now if we have mass of two bodies is same, okay, if we have two bodies having same mass, then p1 by p2 will be equal to v1 by v2, and if we have same velocity, if we have two bodies having the same velocity, then their ratio of the momentum, then the ratio of their momentum will be equal to ratio of their velocities. Okay, then the ratio of their momentum will be equal to ratio of their velocities. Or we can say that if mass is constant, okay, if mass is constant and we have to draw a graph between linear momentum and mass, okay, we have to draw a graph between linear momentum here we have mass, oh sorry, mass is constant, here we have velocity, here we have, okay, mass is same, velocity is same, so it will depend on mass, sorry, my mistake, velocity is same, it will depend upon masses, v is same, so it will get cancelled out, p1 by p2 will be m1 by m2. Okay, so if we have same mass, it will depend on velocities, and how it will depend, it is directly proportional to velocity where mass is constant. Okay, when mass is constant, linear momentum is directly proportional to velocity, and if we have same velocity of variable mass, then linear momentum will be proportional to mass. Okay, when velocity is constant, this will be the graph, and when mass is constant, that one will be the graph. Okay, now how to find change in linear momentum? Okay, how to find change in linear momentum? See, linear momentum is a vector quantity. So how can we find change in a vector? How can we find change in a vector? Delta p vector is equal to final momentum minus the initial momentum. Okay, delta p vector will be equal to final momentum minus the initial momentum. So if a ball is dropped on a surface, and while hitting this surface, ball hits the surface with some velocity u. Okay, ball hits the surface with some velocity u and rebounds back from the surface with some velocity v. Okay, this u and v are the velocities just before hitting and just after hitting. Okay, just before it is hitting, it is having velocity u, and just after hitting, it is having velocity v. So mass, this is a ball which is being dropped. Okay, so this is a ball of mass m, just before hitting, it is having velocity u. Okay, now let us take upward direction as positive, downward direction as negative. We have to take some sign convention. We have to take some sign convention. So write initial momentum. Write initial momentum. What will be initial momentum? Mass into speed into direction will be negative. It is in downward direction, so minus mu. And write its final momentum. We can also write it as, if we write it as P initial is equal to minus mu, or we can also write it as P initial is equal to minus mu I cap or j cap, whatever you want to take. Okay, let us write it in vector form only. And how we will write P final? P final will be, it is in upward direction and velocity is v, so mv into positive I cap. Now calculate the change. So delta p will be P final minus P initial, mv I cap minus initial minus mu I cap. So our delta p vector will be mv plus mu I cap. So delta p will be, mass can be taken out as common, v plus u I cap. Okay, this will be the change. This will be the change in linear momentum. Okay, this will be the change in linear momentum. So whenever you have to find a change in linear momentum, always consider momentum as a vector. When we are finding changes in vector, so it is a vector minus another vector. So write it in vector because momentum is a vector. It cannot be added or subtracted by scalar algebra. Okay, so always write momentum in vector form and then add or subtract. Okay, now let's see Newton's laws of motion. Now what are Newton's laws of motion? In inertia, we discussed that a body in a state of rest will remain in the state of rest. Okay, it has the capacity to maintain its state. And if it's in motion, it will remain in motion because it has the capacity to maintain its state of motion. Okay, so this first law of motion, Newton's first law of motion, is also called law of inertia. Okay, it is also called law of inertia. Now, what law of inertia or Newton's first law of motion says that every body at rest or in a state of uniform motion, okay, every body continues in its state of rest or uniform motion, continues its state of rest or uniform motion in a straight line unless and until it is compelled by some net external unbalanced force. Okay, it is compelled by some net external unbalanced force to change its state. Okay, unless and until we have some force which is changing its state, then only a body can change its state. Otherwise, a body at rest will remain in rest and body in motion will remain in motion in the same straight line unless and until it is acted by some external unbalanced force to change its state. Okay, so we have this as the first law of motion, law of inertia. If a body is in rest, it will remain in rest. If a body is in moving with velocity v, it will continue to move with the same velocity until we stop it by applying some force. Okay, so this is the law of inertia. Now let's see Newton's second law of motion. It states that net external force, okay, it states that net external force applied on a body, okay, net external force applied on a body is directly proportional to the change in linear momentum of the body divided by the time in which the change is brought about. Okay, or we can also say that force applied on a body is directly proportional to the rate of change of linear momentum. Okay, force is directly proportional to the rate of change of linear momentum, and in which direction this force will act or in which direction this linear momentum is changed. If we apply a force F in this direction, momentum will also change in this direction only. Okay, so what it says is it is directly proportional to the rate of change of its linear momentum, and the change takes place in the direction of applied force. Okay, change will take place in the direction of applied force. So rate of change of linear momentum, that is dp by dt. So force is directly proportional to dp by dt. Now remove the proportionality sign, we will add a constant k. Experimentally it is found that this k constant is equal to 1. So from here we will get that force is equal to dp by dt. Okay, rate of change of linear momentum, force is equal to dp by dt, rate of change of linear momentum. Okay, now if my body in delta t time, linear momentum changes by delta p. So what is the average force acting on the body? Average force acting on the body will be equal to delta p by delta t. Okay, or we can also write it as average force on the body is equal to p2 minus p1 divided by t2 minus t1. Okay, this is my average force acting on the body. And for instantaneous force, okay, instantaneous force, what we will have, that force is equal to dp by dt. Okay, force is equal to dp by dt. This will be my instantaneous force. Okay, this will be my instantaneous force acting on the body. Now let's see Newton's third law of motion. Okay, Newton's third law of motion. What does Newton's third law of motion says? It says that To every action there is equal and opposite reaction. Okay, if we push a ball, okay, ball also pushes us. Okay, if we push a wall, wall also pushes us. Same example, if we push the floor, floor also pushes us. Okay, for every action there is an equal and opposite reaction. There is equal and opposite reaction. Now these action and reaction forces, okay, these action and reaction forces always act on two different bodies. Okay, these action and reaction forces do not act on the same body. They always act on two different bodies, and they are acting at the same time. Okay, they always act on different bodies at the same instant of time. Now suppose we have one mass m1 and the other mass m2. We know that this m2 mass will attract 1 by a force F12, like this gravitational force. So 2 will also be attracted by 1 by a force F21 towards m1. Now we know that F1 and F12 and F21 will be equal and opposite. They will be equal in magnitude and in different directions. By gravitational force of attraction, if we have two bodies, one attracts other, the other also attracts the one. Okay, this is the example of Newton's third law of motion, or there are numerous examples of Newton's third law of motion. If you push the wall also pushes us back. Okay, to every action there is equal and opposite reaction. Okay, so these are the three Newton's laws of motion. Now let us do more discussion about the Newton's second law of motion and calculate what are magnitude of forces. Okay, now by Newton's second law of motion, we know that force is equal to dp by dt. Now we very well know that what is momentum, it is mv. So what will be my force? It will be d by dt of mv. What will be my force? D by dt of mv. Whenever we have product of two quantities, how we will calculate the differentiation? First we will differentiate the first quantity. Okay, so dm by dt, differentiate the first quantity, keep second quantity as it is, then keep the first quantity as it is, differentiate the second quantity. So this will be my differentiation. So from here we get the complete expression of the force, that force is equal to, now let us write one more step over here. Force will be velocity times dm by dt plus, what is dv by dt? It is acceleration, so it will become mass into acceleration. Now let's write the complete expression. It will be mass into acceleration plus dm by dt times the velocity. Okay, dm by dt times the velocity of the change in mass. Okay, so this will be our complete expression of the force. Okay, you have seen that force is equal to mass into acceleration, but that's not the complete expression. If mass is changing, we will have complete expression like this. Okay, now let's do its special case when mass is constant. When mass is constant, so when mass is constant, dm by dt will become 0. Differentiation of any constant is 0. So force will become only and only mass into acceleration. Okay, force will become only and only mass into acceleration. Now let's see next case, when velocity is constant. When velocity is constant, force will be equal to, now velocity constant dv by dt will become 0. If dv by dt is 0, dv by dt is 0 or acceleration is 0, velocity is constant, dv by dt is 0 or acceleration is 0. If acceleration is 0, what will be my force? So expression of force will be dm by dt times the velocity. Okay, this will be my expression of force. So these are the two expressions of force when one thing is constant and the other is variable. Okay, now see, force is equal to dp by dt. Okay, force is equal to dp by dt. If we have that momentum changes from p1 to p2 or some variable force is acting, okay, variable force is acting in time delta t, or time goes from t1 to t2, we want to find the change in momentum. Okay, we want to find the change in momentum. We can write dp as f times dt. Now if we want to find the total change in momentum, okay, if we want to find the total change in momentum, what we will do, we will integrate the both sides, that momentum from time t1 to t2, momentum goes from p1 to p2. Okay, so what we will have, p2 minus p1 is equal to integration of f dt from t1 to t2. Okay, integration of f dt from t1 to t2. Okay, so if we have momentum variable, which is variable dependent on t, then we can find force by dp by dt. And if we have variable force, we want to find a change in momentum, then we can find it by integrating f dt. Okay, integrating f dt, this will be the change in momentum. Okay, change in momentum. Now if we are given pt graph, okay, if we are given momentum time graph, momentum time graph is given to us. So here we have time, here we have momentum. It can be anything, okay, it can be any graph. We want to find the force at some instant. What we will do, we will make the tangent, okay, and the slope of this tangent is the slope at this point. Now if we write slope, slope will be equal to dp by dt. We know that dy by dx is our slope, so pt graph slope will be dp by dt. Okay, anywhere we want to find the force, we will draw the tangent, and the slope of the tangent will be equal to the slope of the curve at this point. Okay, so slope will be equal to dp by dt. What is my dp by dt? It is force, so it is force. So what we have is slope of pt graph, slope of momentum time graph gives us force. Okay, slope of momentum time graph gives us force, slope of momentum time graph gives us force. Now if we have force time graph, if we have force time graph, here we have time and here we have force, and this is some arbitrary curve. Now find the area from t1 to t2. Okay, find this area A from t1 to t2. This area A will be equal to integration of f dt from t1 to t2. We know that area is integration of y dx. So this area will be equal to f dt from t1 to t2. What is this integration of f dt from t1 to t2? This is equal to change in linear momentum. Okay, change in linear momentum. So what we have is, therefore, area under force time graph, area under force time graph gives us change in linear momentum. Okay, it gives us change in linear momentum. Area under force time graph gives us change in linear momentum. Okay, this is very important, we have to remember it. Okay, if we have momentum time graph, its slope will gives us force, and if we have force time graph, its area will give us change in linear momentum of the body. Okay, now let's move forward to impulse. What is impulse? Now see, if we have a large force, if we have a very large force acting for a very small interval of time. Okay, if we have a large force acting for a very small interval of time, now see, magnitude of the force is very large and time of action is very small. Can we study the force properly, that how it is varying in this small time? No, it is time interval is very small. Okay, time interval is very small, so we cannot measure how the force is varying or what is the nature of the force which is acting, and it is a large force. If we have force as very large and time as very small, neither we can correctly deduce the nature of the force nor we can measure that very small time interval. What we can measure is product. Okay, if we have a large quantity, say 10 lakhs, okay, if we have a large quantity, say 10 lakhs, and if we have a very small time interval, that is 10 raised to the power minus 5, their product will be 10. What is this? It is a measurable value, it is a measurable value, finite value. If one thing is very large and other one is very small, what we will have is their product will be finite. Okay, their product will be finite. This product is called impulse. Okay, this product is called impulse. So if we have a very large force acting for a very short interval of time, such a force is called impulsive force. Okay, and the product of the force in time is called impulse. Okay, so a large force acting for a short time produce a finite change in momentum. Okay, it will produce a finite change in momentum, is called an impulsive force. Example of impulsive forces can be blow of a hammer. When a nail is embedded into something using the hammer, force is very large, but the time interval for which the force acts on the nail is very small. Okay, blow of hammer, force exerted by bat on a ball is coming, you kick the ball or you push the ball with the bat. What will happen? The time of contact between the bat and ball is very small. Okay, time of contact is very small, but in that contact a large force has been exerted which has changed the state of the motion of the ball. Okay, so this is called impulsive force. And what is impulse? The impulse is the product of both. Impulse will be equal to force into time. Okay, impulse will be equal to force into time. So we can write impulse as F into t, if t is the time interval. Now because F is a vector quantity, so impulse will also be a vector quantity. Okay, Impulse will be equal to force into time. It is also a vector. It is also a vector quantity. Okay, impulse is also a vector quantity. It will be equal to force into time. Clear? Now let us see impulse momentum theorem. What is impulse momentum theorem? Impulse momentum theorem says that if a large force is acting for a very short interval of time, then the impulse imparted to the body is equal to the change in linear momentum of the body. Okay, impulse of a force is equal to the total change in momentum produced by the force. Okay, total momentum produced by the force. This is called impulse momentum theorem. Okay, this is called impulse momentum theorem. Now let us calculate impulse. Impulse is equal to force into time. Okay, impulse is equal to force into time. So if my F force is acting for a short time interval delta t, then impulse will be equal to F into delta t. And what is my force? Force is delta p by delta t into delta t. This will get cancelled out. Impulse will be equal to force. Oh, sorry, change in linear momentum. Impulse will be equal to change in linear momentum. And if we have F force instantaneous, if we have a variable force acting, then short time interval dt, F force is acting in the very short instant of time dt, then small impulse imparted to the body will be di. Small impulse imparted to the body will be di. So total impulse will be integration of f dt. Now we know that what is integration of f dt? It is change in linear momentum. So from here also we have impulse will be equal to change in linear momentum of the object. Okay, impulse will be equal to change in linear momentum of the object. This is impulse momentum theorem. Now let's move forward and do the law of conservation of linear momentum. So what does law of conservation of linear momentum says? If net external force acting on a body is 0, okay, if no net external, okay, if no net external force acts on the system, if we have a system of bodies, or if we have a particular body and net force acting on the body or system of particles is 0, then its linear momentum remains constant. Okay, linear momentum will remain constant. If we have net force as 0, we know that net force will be equal to dp by dt. This will be equal to 0. Now if differentiation of some function is 0, then that function must be a constant. So from here we will get that p vector is a constant. Okay, p vector is a constant. This is law of conservation of linear momentum. Okay, now let us see if we have a system of two particles. Okay, if we have a system of two particles 1 and 2, p1 is the momentum of particle 1 and p2 is the momentum of particle 2. No external force is acting. Okay, f net is 0. No external force is acting. However, they can interact by internal forces. They can have internal gravitational force. If they are charges, they can have electrostatic. Internal forces can be present. And momentum of the system changed. Okay, momentum of the system changed. Now one is having momentum p1 prime and 2 is having the momentum p2 prime. Okay, one is having the momentum p1 prime, 2 is having the momentum p2 prime. So what happened? What happens is initial momentum of the system. Okay, total initial momentum of the system is equal to p1 vector plus p2 vector, and total final momentum of the system will be equal to p1 prime plus P2 prime. This is my initial momentum and this is my final momentum. Now we know that by law of conservation of linear momentum, if net force acting on the system is 0, then initial momentum is equal to the final momentum. Okay, F net is 0. F net is 0. So P initial will be equal to P final. P initial is equal to P final. What is my P initial? P1 plus P2. What is my P final? P1 prime plus P2 prime. Now take all the 1 on one side and 2 on the other side. We will have P1 minus P1 prime. P1 prime is equal to P2 prime minus P2. Now take this. This will become minus of P1 prime minus P1 is equal to P2 prime minus P2. Now what is P2 prime minus P2? Change in linear momentum of 2. And what is P1 prime minus P1? It is change in linear momentum of 1. So from here we will have delta P2 is equal to minus of delta P1. Okay, change in linear momentum of 2 is equal to change in linear momentum of 1. So if one loses some momentum, other will have an equal amount of gain in the linear momentum. Okay, so total momentum will be conserved, and if one's momentum changes by P1, if one's momentum changes by some delta P amount, if it has gained, other will lose. If other one has gained, this one will lose. Okay, so this is law of conservation of linear momentum. Now by application of this law of conservation of linear momentum, we can calculate the recoil velocity of a gun. Okay, now we know that when a gun is fired from a bullet, what happens is the bullet sorry, I'm really sorry. When a bullet is fired from a gun, what happens? The gun recoils backward. Okay, initially what is our system? Initially this is our system, both the bullet and the gun. Okay, both the bullet and the gun are at rest. Okay, initially both are at rest, but when bullet is fired, bullet start moving with some velocity u. Bullet starts moving with some velocity u. Let us say that gun also gains some velocity v. Okay, if m is the mass of my bullet and capital M is the mass of gun, no net external force is acting on the system, so P initial will be equal to P final. What is initial momentum? 0. Gun is also at rest, bullet is also at rest, so initial momentum will be 0. What is final momentum? Momentum of bullet is m into u and momentum of gun is m into v. So from here we will have mv is equal to minus of mu. Take mu to that side, mv will become minus of mu. From here we will have velocity of gun will be equal to minus m by capital M into the velocity of bullet. Okay, into the velocity of bullet. Now because m is smaller, okay, because small m is less than capital M, so v will be less than capital U. Okay, v will be less than capital U. Gun will recoil backwards but with a lesser velocity. It will recoil backwards but with a lesser velocity. Negative sign shows that velocity of bullet is opposite to the velocity of gun, or we can say that negative sign shows that velocity velocity of gun is opposite to the velocity of bullet. Okay, so this is the recoil of gun, which is an application of linear momentum's conservation because no external forces acting on the system. Now let's move forward to normal reaction. Now what is normal reaction? Okay, let us see. We have a situation. We place a block of mass m on the ground. Okay, we place a block of mass m on the ground. What happens is earth will attract this block by a force mg. Earth will attract this block by a force mg. Okay, so when we drop a thing, it goes down due to which force? Mg force, earth's gravitational force. If the block is on the surface, then also mg force will be acting on this block downwards. Now due to mg force, this block tries to penetrate in the ground. What happens is, due to mg force, this block tries to penetrate in the ground. Now when two surfaces come in contact, okay, two surfaces come in very near contact, okay, what happens is atoms of one surface are very near to the atoms of other surface. So there will be electronic repulsions as well as attractions. Electrons will be attracted to the nuclei and electron will repel each other. Obviously, this surface is trying to penetrate into the other surface, but no surface will allow to penetrate. No two atoms will allow to penetrate into each other. Will atoms allow to penetrate? No. So what happens is, this surface, second surface, pushes the first surface with some upward force. Okay, what happens is, the second surface pushes the first surface with some upward force. This upward force is called normal reaction. Okay, this upward force is called normal reaction. Now 2 will exert a normal reaction on 1. Okay, how normal reaction? Normal reaction will only act if there is some action force present. If there is some action force present. Okay, if there is some action force present, normal reaction will only act if there is some action force present. And how normal reaction act? It always acts perpendicular to the surfaces in contact. Okay, it always acts perpendicular to the surfaces in contact. Like these two surfaces are contact, normal reaction will be like this. If these are the surfaces in contact, normal reaction will be perpendicular to the surfaces in contact. Okay, so what is normal reaction? Whenever we have some action force, it is just like if we push the wall, wall also pushes us. Wall will push us only if we push the wall. So normal reaction exerted by wall on us will be present only if we exert some force on the wall. Okay, that's why it is called normal. Normal means perpendicular, and reaction because it is a reaction force. It will act only if there is some action force. Due to this mg force acting on the block m, it tried to penetrate into the ground. So ground will not let it penetrate. It will apply some upward force. That is the normal reaction. Now let us see if this normal reaction, if we have a block of mass m kept on the earth, are this normal reaction and mg action reaction pair? Are mg and n an action reaction pair? Are mg and n an action reaction pair? So what happens is, mg force is acting on which body? this body. And normal reaction is acting on which body? Again mass m. Action and reaction do not act on the same body, okay? Action and reaction act on different bodies, okay? But these two forces are acting on the same body. Action and reaction act on different bodies, but these two are acting on the same body. Mg and N are acting on the same body. So they are not an action reaction pair, okay? They are not an action reaction pair, okay? Mg and N are not an action reaction pair because they act on same body, okay? Now let us move to tension force in a string. Now what is my tension force in a string? So when we have a rope or anything tied to some body, when we pull this rope, what we are trying? We are trying to separate the molecules or atoms of the rope. But atoms are also attracted by forces of attraction, so they don't want to separate. A force will develop in the rope, along the rope, which is called tension, okay? So tension is defined as the force transmitted through a rope, string or wire when pulled by force acting from opposite sides, okay? When pulled by force acting on opposite sides. So if we have this a string or a rope like this tied to some end, and if we pull this end by some force F, so what will happen? A tension will develop, okay? A tension will develop sorry, a tension will develop in the force which is called tension. A force will develop in the rope which is called tension force. Let us take one more example. Suppose we have a block of mass m hanging from the ceiling, okay? We have a block of mass m hanging from the ceiling with a rope. What will happen? Mg force is acting on this block downwards. So block is trying to push the rope downwards. Every action has an equal and opposite reaction. If we are pulling the rope downwards, rope will also pull this block. Rope will also pull this block upwards. So the tension T will act on the block in upward direction, okay? We are pulling the rope downwards, so a tension force will develop. So a T will act also. So T force will act upwards on the block, okay? We are pulling the rope also tries to pull, okay? And how much force will be developed? It will be equal to mg, okay? Tension will be equal to mg because block is at rest, so upward force must be equal to downward force. This is called tension. Now see next what is. It is free body diagram. What is free body diagram? If we draw all the forces acting on a body, so if we have a body and we draw all the forces acting on this body, then that diagram is called free body diagram, okay? That diagram is called free body diagram. So if we have a mass m, okay, which is lying on the ground, what we will have? Mg force is acting on this body downwards, normal reaction is acting upwards. This is the free body diagram, okay? This is the free body diagram. If we have an inclined plane theta, of inclination theta, and a block of mass m is lying on this plane, how many forces are acting on this block? One force will act mg vertically downwards, other force will act perpendicular to the plane, normal reaction. Now let us resolve this mg into two components. If this angle is theta, this angle will also be theta. So this component will be mg cos theta, and this component will be mg sine theta. So this will be my free body diagram of the block. Okay, this is free body diagram, representation of all the forces acting on the block. Now let us see what is equilibrium. If all the forces acting on a body sum up to 0, okay, if the vector sum of all the forces acting on the body comes out to be a null vector, then the body is said to be in equilibrium. Okay, so when net external force acting on a particle is 0, okay, when net external force acting on a particle is 0, then the particle is said to be in equilibrium. Okay, if we have a particle and multiple forces are acting on this particle, okay, multiple forces are acting on this particle, let us say F1, F2, F3, and the vector sum net external force will be F1 plus F2 plus F3. If this comes out to be 0, then the particle is said to be in equilibrium. So what is the condition for a particle to be in equilibrium? F net vector must be 0, okay, then the particle is in equilibrium. But for a rigid body, torque must also be 0. For a rigid body, net external force as well as net external torque both should be 0. So if we have a rigid body like this and I am applying some force F in this direction and some same amount of force in this direction, net force is 0, F in this direction and F in this direction. But what will happen? As soon I apply a force in this direction and this in, body will start rotating. Body will start rotating, so it will have some torque. So for a rigid body, net force as well as torque must be 0. Now there is a theorem in which we can deal with objects at equilibrium. So if we have a particle in equilibrium under the action of 3 concurrent forces, okay, what are concurrent forces? Having the same originating point or terminating point. Okay, so if we have a 3 concurrent forces F1, F2 and F3 which are acting on a particle, and the angle between F2 and F3 is alpha, okay, F1 and F3 is beta and F2 and F1 is gamma. Then Lami's theorem says that F1 by angle between the other two forces, okay, F1 divided by the sine of angle between the other two forces. So sine of alpha is equal to F2 divided by sine of the angle between the other two forces beta will be equal to F3 divided by sine of angle between the other two forces gamma. This is called Lami's theorem. Okay, this is called Lami's theorem. Lami's theorem is only and only applicable if the object is in equilibrium under the action of 3 concurrent forces. These are the conditions. Then only we can have this Lami's theorem. If we have a particle in equilibrium under the action of 3 concurrent forces, then we will have that F1 by sine alpha is equal to F2 by sine beta is equal to F3 by sine gamma. Okay, this is Lami's theorem. Now let us see motion of connected bodies. Okay, motion of connected bodies. So if we have two bodies of masses m1 and m2, these are connected by a string. Okay, these are connected by a string and a force F is applied on this block. Okay, force F is applied on this block. What will happen? As we apply the force, a tension will develop on the string, which will act backwards on m1, and same tension will act forward in m2. Tension will remain the same as tension will remain the same when the string is same. Okay, until and unless string is same, tension will remain the same. So tension T is acting backwards on M1 and same tension T is acting forward on M2. Now because F force is acting, system will accelerate forward. Okay, because F force is acting, system will accelerate forward. What will happen? If M1 is moving with A acceleration forward, M2 also has to move with the same acceleration because they are connected by the string. Now draw the free body diagrams of both the blocks. We have M1 acting in the forward direction by force F and tension T backward, and M2 is having tension T acting on the forward. Both are moving with acceleration A forward. Okay, now write the equation of motion. Equation of motion will be net force is equal to mass into acceleration. So what is my net force? Applied force minus T will be equal to M1A, and in second case T will be equal to M2A. Now we have to find the acceleration and tension. So add 1 and 2. Okay, if we add the equation 1 and 2, adding 1 and 2, what we will have? Tension and tension will get cancelled out. M1 plus M2 into A. So from here acceleration will be F divided by M1 plus M2. Okay, acceleration will be F divided by M1 plus M2, and tension will be M2 times A. So tension will be M2 times F divided by M1 plus M2. Okay, tension will be M2 times F divided by M1 plus M2. This will be the acceleration of the system and tension in the string. Okay, so now let us see one more system. If we have a block of mass M1 and a block of mass M2, and we applied a force F on this M1 block. Okay, we applied a force F on this M1 block. So what will happen? Due to this force, whole system will move with acceleration A. Now when M1 moves with acceleration some forward, it will what happen? It will push M2. So a normal reaction will act on the M2 in forward direction. Okay, if normal reaction, if M1 is pushing M2 with force N, M2 will also push M1 with force N, but in opposite direction. Okay, so normal reaction will be acting. Now draw the free body diagrams. M1, one F force is acting forward and N force is acting backward, moving with acceleration A. Okay, now draw it for M2. Normal reaction is acting forward, moving with acceleration A. Write the equation of motion. So first equation will be F minus N is equal to M1A, and next equation will be N will be equal to M2A. Now if we add both these equations, F will be equal to M1 plus M2 into A. So from here acceleration will be F divided by M1 plus M2. Acceleration will be F divided by M1 plus M2, and normal reaction is equal to M2 times A. So it will be M2 times F divided by M1 plus M2. This will be the normal reaction acting between the blocks, and this is the acceleration of the system of blocks. So this is motion of connected bodies. Okay, now let us do mass pulley systems. Okay, now let us do mass pulley systems. In mass pulley system, first system is our Atwood's machine. Okay, first system is our Atwood's machine. Now what is an Atwood machine? If we have a pulley, a massless pulley, okay, if we have a massless pulley, and on this pulley, on this massless pulley, we have two masses M1 and M2 hanged by a ideal massless string. Okay, this is a massless pulley and masses are hanging on this pulley with the help of an ideal string. So if m1 is heavier than m2, if m1 is heavier than m2, what will happen? m1 g force is acting on this block downwards and the tension will develop upwards. So it is moving down with some acceleration a. If this block is moving down with acceleration a, this block will move up with acceleration a. Force acting on m2 is m2g downwards and tension T upwards. Okay, if tension T is developed in this string is T. Okay, T will always act away from the body. Okay, if this block tries to pull the string down, string will pull it up. So force on block will be upwards. Same, we will have tension T here, same tension T here, and again tension T here. Now draw the free body diagram we have drawn. Write the equation. First equation will be mg minus T is equal to m1a, and second equation will be T minus m2g is equal to m2a. Add both these equations, we will have m1g minus m2g is equal to m1a plus m2a. So from here, acceleration will be equal to m1 minus m2 divided by m1 plus m2 into g. This will be the acceleration of our Atwood machine. Okay, this will be the acceleration of our Atwood machine. Now substitute in one equation and we will get the tension. So T is equal to m2g plus m2a. T will be equal to m2g plus m2a. Substitute the value of acceleration, which is m1 minus m2 divided by m1 plus m2 into g. Now when we take the LCM will be m1 plus m2, g will come out as common, so factors will get cancelled out. What we will left with be 2 m1 m2 into g divided by m1 plus m2. Okay, this will be the tension in the string. Okay, this is the tension in the string and this will be the acceleration of the blocks. Okay, this will be the acceleration of the blocks. Now let us do one more mass pulley system. Suppose we have a block. Suppose we have a block of mass m2 and a table. On this table we have a pulley connected. Okay, on this table we have a pulley connected. So this block is connected to some m1 block hanging from the pulley. Okay, what will happen due to this m1 block? What will happen? Its weight m1g is acting downwards. m1g will push the whole system or pull the whole system downwards. So it will move with some acceleration a downwards. If this block comes down with acceleration a downward, this has to move forward with the same acceleration a downwards. What happens? A tension T is acting, same tension T will be acting over here. So write the equations. For first body, we will have that m1g minus T is equal to m1a. Okay, for second block we will have T is equal to m2a. Add both these equations. m1g will be equal to m1 plus m2 into a. So from here, acceleration will be m1g divided by m1 plus m2. Okay, acceleration will be m1g divided by m1 plus m2. Substitute in 1, we will get that m1 m2 into g. Substitute in this equation, multiply this by m2. So this will be my tension in the string. Okay, this will be my tension in the string. By using the same concept, we can do a lot of mass pulley systems and a lot of connected body problems in which there is some connection, either string or pulley or direct contact, anything. We can do also pulley on inclined plane by following the same steps. Draw the free body diagram, write the equation, solve it for variables. We will get the mass and accelerate, or we will get the acceleration and tension in the string if there is string, or we will get the normal reaction if it is direct contact, and acceleration of the system. Okay, so this is all about chapter Newton's laws of motion. I hope you enjoyed the quick recap of this session. So keep studying, keep rocking. All the very best to all of you. Okay, thank you everyone.